Hello everybody. In this video I shall show three little programs which operate by means of what I call fragmentation sets in order to show the similarity of patterns. They will be just little toy demonstrations in order to show you a general principle which I regard as quite powerful. The first example will be to compare two images. The second example will be concerned with the recognition of typing mistakes. These two examples will be both written in Scheme, and the last example will be a function in Haskell to just show you the similarity of two patterns and let you do with it whatever you want. Let's proceed to the first example. Two pairs of patterns will be shown, and it will be compared where there is the greater similarity. That may be helpful if you want to know whether a picture can be rather categorized as X or rather categorized as Y. In this case, a number will be shown and the system will be asked to say, is it more similar to a known example of 1 or is it more similar to a known example of 7? There we go. So, this is the first pair. This is the number shown to the system, so to say. And this is the number which the system already knows. Let's say it knows that anything similar to that is a 1. So what is this? Is it a 1? It's not exactly a 1, but it has a lot in common with a 1. In particular, if you decompose this into sub-patterns, many of these sub-patterns will be similar to the sub-patterns obtainable from this number. The sub-patterns here are two-dimensional because we are looking at a two-dimensional pattern. So, any possible representation which would fit within this pattern is compared with any possible representation of a sub-pattern in here. Those which are the same are counted towards the similarity, and in this case we are getting a similarity value of 168. That means 168 sub-patterns have been found to match, and in that sense this is the value of their similarity. Notice that this is unlike a set representation. A set representation would simply say, well, how many X's are there? Or even in a worst case, do both images contain an X? And yes, they do. But it won't say in what way is this X distributed. A sub-pattern does keep some structure. For instance, if you're looking at, let's say, this for instance, you can say there is a underscore, an X and an underscore precisely in these positions. Now, if you look at it as a vector would say anything that isn't in its position means things are different. So if you would just simply shift a vector along its dimension or dimensions by even one position, if you then compare position by position, you will say they are totally different, which is intuitively not true. You can say that this one is a little bit more towards the right than this one, but it's not a totally different figure due to that. So I believe that looking at the sub-patterns in what I call fragmentation sets is better than either making a pure set comparison or making a vector comparison. So here we have a similarity value of 168. Let's look at the other two numbers. You're having here the same 1, but now a 7. And the common sub-patterns also can be found, but only 156. And in that sense, you could let such a system decide that this task is more properly categorized as a 1 than as a 7. That was the first experiment. Second experiment begins now. Let us say you're having a set of known words. Let's say these ones, okay? And anything which the user types must be one of those words. If it's not, you can say most likely he has mistyped. Alright, I have here only some 6 words, but it could as well be 600,000 words. Doesn't matter, just the principle is important. So I have created here a function named try_word, and it is telling whether there is a suggestion. If the word is so entirely different from anything known, then the system can actually not propose you anything at all. But it does match rather nicely if you have just mistyped a little, which is what people usually do. You could extend the system, obviously. You could show not only the closest match, but let's say the closest 3 matches or whatever else you want. But you could implement in this way a typing correction, let's say a type checking for an editor. Now what would happen if you input a valid word but the system doesn't know it? Well, then this word, from the point of view of the system, is not valid. I'll give you an example. Try word elephant. Suggestion apocryphal. Because elephant may be a valid word, but it's not in the dictionary. When it looks at words and compares how similar they are, it looks at every possible substring of a word. In this program I have created a function which is called all subchains of SUMList. Let's say all subchains of apple. Oops, yeah, sure. Should comment that, obviously. I quote it out. And there you go. Apple is one pattern, but apple and pupil and so on, these are all possible subchains which can be found within this word. This obviously can become rather involved. If you say elephant, you're going to get, of course, a lot further subchains. Again, notice, this is not just a pure set comparison. For even if you say that this is just one subchain of the entire word, it is still ordered. So you keep some ordering in this comparison. Well, that was it with the second experiment. And now comes Haskell with a function of judging the similarity of 2 integer lists. Alright, yep, there we go. Load sf2.hs. Done. I have called my function quite properly similarity. Let's first test it on 2 lists which are exactly the same. 2, 3, 4, 5. There we go. It tells the similarity between those same lists is 150. What happens if I extend one list? Well, then it judges that, well, there is a degree of similarity, but there is a punishment as the lists are not of equal length. The same thing will be observable if I make the second list shorter than the first. Similarity is just 16. So what happens if I change one number? I'm going to say like that. The 1 changes into a 6. The similarity is then only 100 instead of the perfect 150. What would happen if I change one number, but I change it in the middle? So the 3 becomes a 6. This cuts through a lot of longer subpatterns. And now it says the similarity is only 60. This is obviously just one possible way of implementing it, and I leave it to you what you regard as most suitable. But here you do have a flexible way of judging whether 2 patterns are similar or not. Well, that is all for now. Thank you very much for watching. I wish you much success in your artificial intelligence experiments, and I would be happy if this could be helpful for you. Thank you very much for watching. See you soon. Goodbye.